Okay, to begin with, I'm going to show you why the cross product formula is what it is. And hopefully this year I'm going to get it right.
Oh,
I think I will. But so part of this goes with we're going to do things in terms of the how it is in the formula packet, but I believe the formula packet uses this as V1, V2, V3. And this is going to be a three-dimensional vector V and W. And what we're going to do is V cross W. And you do have to use an X for multiplied this way. And essentially what I've got is V1 I hat plus V2 J hat plus V3 K hat. And I'm multiplying this by W1 I hat plus W2 J hat plus W3 K hat.
so
And so this involves some foiling. And so what you do is you do V1 times W1 I hat cross I hat. And I'll show you what this cross means. Yes, this is very tedious. It's a nice thing that they gave you the formula. Yeah, those are ones. W1. The order that I'm doing these crosses matters. So because it's this times this, it's J hat cross I hat. Aren't you glad you don't have to do this every time? V2 W3. I should just make these nicer. J hat cross K hat plus V3 W1 K hat cross my hat plus V3 W2 K hat cross J hat plus V3 W3 K hat cross K hat. So now we're going to talk about what these hats mean. So we use the right hand rule, and we can think of this on a sheet of paper and try to hold it up. The right hand rule uses your right hand. You point your hand in the direction of the vectors. So when I'm looking at I hat cross J hat, I go towards the X, turn toward my fingers towards J, which is Y, towards positive J, and my thumb points in the direction of the vector, that's K. So I hat cross J hat is K hat. There is a little shortcut to this, little trick here. I, J, K. I cross J equals K. J cross K equals I. I cross K, if I go backwards, is negative J. So it's all about which way I'm rotating. And the beautiful thing here, I cross I cancels out. J cross J goes away, and K cross K. Oh, then I can't read at the end. Completely cancels out.
So I plus J
Equals K. And I can show that with the right-hand rule.
cross
I cross K, if I do like this on the graph, K is going to be curving up off the page, equals negative J. So the right hand, when I'm looking at this, I start in the direction of the first one. So I'm looking at this I cross J. Point my hand on the graph in the direction of positive I, which is positive x-axis. Curl my fingers towards J, positive y-axis. Your thumb points in the direction positive K, up out of the page. So positive Z. If you do J cross I, start with your hand, y-axis, positive. Turn towards positive I. You got to flip your hand upside down to do that. Negative K. That is the right-hand rule. It's weird. Yes. That's why I like this. But that right-hand rule becomes necessary when you get into advanced physics and you're just talking about vectors that are not in eyes. Sometimes not. Yeah, there are. So I've got I cross J and that's K. So V1W2 K hat plus V1W3 I cross K is going to go this way. So that's positive J. No, that's negative J. That's going. So for the negative, I'm just going to put it in front. Okay, that makes sense. Negative J hat. Plus my next one, V2W1, J cross I is negative K. V2W3, J cross K is positive I. V3W1, K cross I is positive J. V3W2, K cross J is negative I. Nothing cancels out anymore. But when I put it into a matrix, which is how they're going to show it in your IB formula packet, V2W3 minus V3W2 is going to be my first thing in my vector. J V3W1 minus V1W3 and K V1W2 minus, what's the other K? V2W1. This is V cross W. Don't have it handy, so I'm going to go ahead and pull it up. Having a formula.
Also,
Yeah, having the formula is very helpful. Okay, so mhm, when you multiply vectors, we'll take a look. So here is your cross product formula that we just did. So let's say I put in two vectors on my calculator. To do vectors, I have to do 3 by 1, and we'll call them V and W. And I believe in just putting them in and storing them. Vectors, not matrices, just vectors. Vectors being essentially a one column matrix. Mhm. And I'm totally a fan of this store them as letters, so you don't have to. Now, menu, matrix, and yeah. It's menu, matrix, and vector. Vector. You have cross product or dot product. Cross product, and I think to do cross product, you do VW. And notice that the cross product gives you a vector. It's called the vector product. The dot product gives you a scalar. Notice the scalar product. So that is why the cross product formula is what it is. Whenever it loads, we'll do a couple examples with it. No. The scalar product, hold on. Yes. That's the vector product. The scalar product gives you the magnitudes multiplied times the cosine of the angle between them. So if I'm looking at that, it looks like it's this. So it's not just the magnitude of the new vector. It's kind of a weird thing. It, the main thing it's useful for is finding the angle between them and using this formula. You use that a lot. And if the angle between them is 0, they're parallel. Well, yeah, if the angle between them is 0, if the dot product equals 0, the cosine of 0 is 90 degrees. So that means they're perpendicular or orthogonal in three-dimensional space. That's where it becomes super useful. Becomes useful when you're having to in several different applications. So maybe we can get here to the vector product one of these days. It'll load. Okay. This idea with the right-hand rule. Again, you twist towards V so they're going in. This is actually useful on bolts. You point with bolts or screws, you point your thumb in the direction that you want to go, twist your fingers, you have to twist the bolt or screw that way. So I want it to go into the table, thumb down, twist my fingers around, I twist in the direction from hand to fingers. Twist the opposite way. So Y, U and V and W. Vector products are not commutative. Okay, that's true. Remember that was true with matrices. The order you put them in, yes, does matter. And where does my pen go? No. The yeah, the okay, so using this vector product, this lets you move around some vectors. I'm gonna pause the recording. Those watching the recording, pause it and watch this video. So understanding the perpendicular to the plane through the two vectors is really important. And the right-hand rule that going along the first one turning tells you whether it's parallel or the anti-parallel vectors being opposite directions. So that's where the right-hand rule, your thumb might not point perfectly there, but you know it's perpendicular to that plane. It tells you, the right-hand rule tells you whether it's essentially up or down, left or right, depending on how the plane's lying. So finding a cross product. We get this formula. You have that in your formula book. That's what we developed. We use the right-hand rule to tell us the direction. But when I'm finding this, I'm just gonna look at my formula. So I'm gonna write my formula on the side so it's easy to see. And we know that this is V cross W. So I look at my two vectors. My specific case, I guess I'm gonna go above them. Is V2 is 1 times W3 is 1 minus V3 is 3 times W2 is -2. And that's 1 plus 6 is 7. Then V3 W1 minus V1 W2. 6, 3 negatives is still negative. 6 minus 4 is 2. And then V1 times W2. V2 times W1. 4 minus 2 is also 2. I screwed up a negative sign? No, I screwed up. V1 is -2. Oh, W3. I screwed up plugging them in. Make sure you can plug them in correctly. That's 8. Your calculator can do this. I don't believe you get to use that feature on your calculator on the test. I think the vectors feature gets shut off. Not the complex number stuff, but all the, I believe the cross products. Yeah, you can convert to complex and polar. So find a vector of length 3 that is perpendicular to both of these. So what's perpendicular to both of them? The cross product. Right. I do not want to get rid of that. I still want my formula. So I'm going to do a cross product here. So V2, 1 times W3 is 1 minus V3 times W2 is -2. 1, that's also 7.
Since this is a perpendicular vector, you can do either, right?
You could do either direction, yes. V3 is 3, W1 is 2, minus V1 is -2, W3 is 1. This might be the same vector. I feel like these are the same vector that we just did, just written in a different form. V1 is -2, W2 is -2 minus V2 is 1. W1 is 2. Yeah, that's the same vector. It wants a vector of length 3. So we've got our cross product, but our cross product is way longer than 3. Multiply by 3. Yep. So 49 plus 64 plus 4. I'm gonna just use a calculator to add the heads. So to do a unit, that's square root of 117. To do a unit vector, we would do 1 over. So to use unit length 3, I'm just going to do 3 over. And okay, they gave it in IJK form, which probably makes sense because it was given in IJK form. And you have to write the hats because you can't write in bold. So a unit vector is essentially just dividing by the magnitude of the cross product. That's all this formula is saying, is that your unit vector is the cross product divided by its magnitude, just like any unit vector. That's just a unit vector, I guess that's perpendicular. So consider these 3 points. Find AB cross CB. Do I have more in this section? I guess so. AB cross CB. Well, I need to find AB, and then I need to find CB. So AB is going from, that's
The dot product.
-2.
Wait.
So I'm doing the cross product of these 2 vectors, but AB is the vector from A to B, from 1 to -2. Not yet. 1 to 1 is 0. Yeah, that's why, because this is new. CB, -2, 2, 0. And I need to look up my formula again because I erased it. V2W3, V3W2. Okay, there is a logic to this formula. Just a second. So I've got my formula again. So V2, 1 times W3, 0, minus V3, 0, times W2, 2. That's convenient. That's 0.
Next one is 12.
0 times W1 is -2, minus V1, 2, 0. Yes, 0. And V1, -2 times 2 minus V2, 1 times -2 is 6. Right, -4 plus 2. No, that's -2. +2.
Oh, wait. The one is negative. It says. T minus 1 is
Oh, CB, I totally did the wrong vector. I did CA. Or I did AC. CB goes from C to B, -1. -1 to -1 is 0.
wait, so you did AC.
Yeah, I did AC. 2 to 3 is 1. B to 1 to 1 is 0. So I guess that means I need to change these. V2, W3, 3, W2 is 1. It still comes out to 0 there. W1 is 0. Right. And then V1, W2 is 1. V2, W1 is 0. Wait, this is -1. So it becomes +2. Okay. Helps, very important to do each step correctly and pay close attention. Because there's a lot of room to make mistakes on these. So area between two vectors, the magnitude of the cross product is defined as the area covered by the two vectors, or essentially the parallelogram area.
Well, what?
The magnitude of the cross product
Mhm.
is essentially this area of the parallelogram formed by
Interesting. Oh, A.
mhm.
Or A.
So A cross B is the magnitude of the area. That we would get by adding A and B. So that's how they got this formula here. Area equals magnitude of B times magnitude of A, I don't know,
Oh, so it's about magnitude.
times sine theta. No. Well, it's magnitude of A times magnitude of B. You have to do the magnitudes first. Yes. So, and area of a parallelogram is just base times height. But height, if you look at the triangle, is magnitude of A sine theta. And that's how they're developing this formula. Length of base is magnitude of B. So, find the exact value of the sine of the angle between these vectors. Okay, so it doesn't give me it gives me the cross product. So the area is the magnitude of the cross product, which is 1 plus 4 plus 9 is square root of 14. The magnitude of V is 2, magnitude is 3, sine of the angle between them. And all it asks me for is the exact value of the sine, not actually the angle. So sine of theta equals square root of 14 over 6. Magnitude of the cross product is the area. So area equals magnitude of cross product. Area also equals this. So something they love in IB is you got two different things, set it. Yeah, you can use one to find the other, find one part, use that to find the other thing. And notice I read the directions that asked me for the sine of theta, not theta. So here's a quadrilateral. Show that the quadrilateral is a parallelogram and find its area. They decided to do AB and DC. It wasn't AB. Oh, okay. So if I'm looking at A, B, C, D, and if I want them to be parallelogram, AB should be the same vector as CD. That would show those are parallel, which when we found the vectors, they're equivalent. So those two sides are parallel. We would need to show that. I guess actually there's a property of parallelograms. I don't need to show the other sides. But if they are equivalent in length and in the same direction, so equivalent vectors, you don't need the other side. If you have parallel and equal length, you have a parallelogram. That's one of the properties from geometry. But you could always find, if you needed to prove it, you could find BC and AD, find that they're parallel and equivalent. So it wanted me to find the area. So then if I do AB cross BC and find its magnitude, that's the area. That kind of makes sense. Since we're running out of time, I didn't want to actually go through the calculation. The area of a parallelogram formed by two adjacent vectors is 4. Find the value of x. So I have my two vectors. X1, -1. And 1, 1, 2. cross product, I'm crossing them.
Oh, it looks like it says,
Not a cross, not a multiply. So V2W3. V2, 1 times 2 minus V3, 1 times 1 equals 1. V3W1. What's V3? That's a -1 times W1 minus V1x times W3, 2. -1 minus 2x. And V1x, W2 is 1 minus V2 is 1, W1 is 1. Okay, and it told me the area was 4. So I know 4 is equal to the magnitude of this. Which means I have to square these things, which is going to be slightly annoying, but to solve, I'm now going to go to a place where I've got some blank room. To solve, I'm going to square both sides, get rid of my square root right away. 1 negative is 2x, that's 2x plus 4x plus 4x squared. I'm going to combine like terms. 5x squared plus 2x plus 3. I'll set it equal to 0. 5x squared is 2x minus 13. And I would solve this by graphing because I don't feel like using the quadratic formula. I'm so glad that they didn't actually reduce down to a quadratic. I'll check that I get the same thing with my calculator.
right? Is that okay?
I get different answers. Did I square it wrong? One squared. I think it's 7. Oh, they have a different cross product.
That's not the sign.
V1, W3. They messed up a sign, yeah. There's got to be it. And so that would, change all of these values. Nine. So 11, -5. Now I get the same values they have. So it's very important to be very careful with your cross products. Components of vectors. So making things in component form, find the component, consider A, find the components of A in the direction of B in the plane formed by two vectors. So to find a component of a vector, so it's basically saying if W is my direction vector, yes, he's not here. Yes. So V, the component is basically, usually we do components in the direction of X, Y, and Z. You can do components in the direction of another vector. I tend to kind of think these, well, you use them in physics, but what we usually do is we just pretend to tilt the axes.
Well, yes, so I don't know between W and D, so.
So what I'm doing is I'm taking V and I'm making it components along the direction of W and perpendicular to W.
So it's one time W into your, it's like a tilted axis.
It's like a tilted axis. Yeah. Yes. So you just do the magnitude of this V vector times the cosine gives you the parallel, and the perpendicular is magnitude of V times the sine. That makes sense? So when we look at this example, I guess there's a shortcut to do. You can use A. He's not here either. So
You're one away.
So the component of V in the direction of W is V dot cosine, magnitude of V times cosine theta, or V dot W, because we had this formula. So if you divide it by magnitude of W, you get that. So this is where the dot product becomes useful again. So A dot B, 0 plus 2 plus 2 is 2 times 2 is 4 is 6. Magnitude of V is square root of 8. The component of A in the direction of B is then the dot product divided by the magnitude, or this. So yeah, a lot of times in physics, we just tilt our axes and do components on the tilted axes. Yeah. So there's you're taking this formula, and if I'm doing component of V in the direction of W, I end up with
like
this.
component. So like V is the new x-axis.
W is the new x. is the new x-axis.
Oh, and that makes more sense. And so we're finding. Okay.
We're finding essentially how long along the W direction is V. Kind of, yeah. You can do it with trig, but this formula becomes very handy and faster. Yeah, the magnitude parts, the angles. So the angle between two vectors A and B is 1.2 radians. Find the component of A in the direction of B. So
basically on the x-axis.
A is something above it. So find the component. So we know magnitude of A is square root of 2. And I believe I can do square root of 2 cosine of 1.2. Yeah. The angle between two vectors A and B is 30. Find the component of A perpendicular to B in the plane. Okay, so the perpendicular component is going to be sine.
Wait, find the component of A perpendicular to B.
So B's here, A's parallel in the direction or parallel. So we're doing a sine. Square root of 9, 11. Sine 30 is 1/2. I don't have a clue why they went to sine 1.2. But that might be a typo. Because yeah, their answer is yeah, their answer just no. Their answer still doesn't work. That was a typo in their thing. This should be a 30. Last thing. Consider the vector A, the component of A in the direction of B in the direction of vector B in the plane formed by the two vectors is 1.3. Find the angle between the vectors. So this is vector A. The is 1.3.
So we can have the magnitude are one of the widths.
So we know that this is 1.3. This is going to be square root of 2.
Inverse cosine.
Or cosine, yeah. And radians, it's 0.404. Give your answer to the nearest degree. So I guess I should do it in degree mode. 23 degrees. And that is it for that lesson.